This is a very interesting problem based on superconductors and mutual inductance. Okay, so probably this will something new for all of you. There are two superconducting loops with self-inductance L in opposite sense. Okay, there are two superconducting loops, self-inductance is L and current is in opposite sense I, and they are at far away point. If M is equal to L by 2, coefficient of mutual inductance is L by 2, then what is the work done in bringing them closer? Okay, so this is the question. So let's start analyzing it first. There are two superconducting. First of all, what is a superconducting loop? The superconducting loop is a loop, you can say basically it's in quantum mechanics, but you can say that it is a loop in which there is resistance is zero, right? Resistance is almost zero, superconductivity. So superconducting loops is basically that. Or probably if there is a superconducting loop, then the logic is the flux will remain same through that loop. So this is the logic of superconducting loops, okay? If you were unaware of it, you can remember it now, that in superconducting loop, basically the flux remains the same, okay? So now let's start. There are two superconducting loops with self-inductance L in opposite sense. So there is, like, let's say one loop, there is another loop, identical loops we are assuming, because self-inductance is L. Now they are at far away point. Distance between them is, let's say, infinity. If they are at far away points, the mutual interaction will be zero. Okay. So now what will be the energy? Let's say current is I here in this direction, current is I here in this direction, opposite sense is there. But since there is no interaction, it does not matter which sense is current rotating in. So energy initial is equal to 2 times half L I square. So this is the initial energy that we know, L I square, right? L I square is the initial energy combined. Why we are finding energy? Because work done is equal to change in energy. Work done is final energy minus initial energy. So initial energy we have already got. Now comes the most important point of finding the final energy. So what will be the final energy? Now see. First of all, the flux should remain same, but the current will change. So let's say for any one coil, if I draw like this, now the current will not be same because there is another coil also and current is in opposite sense. Now since they are identical, let's say if current in this has become I dash, so current in this will also become I dash, because everything is identical. Now the flux should remain same. Through any one coil, the flux should remain same. So let's analyze this coil. Initial flux is equal to final flux. So what is the initial flux? Flux is equal to Li. So initial flux is equal to Li. Now what is the final flux? Now if current is I dash, so one of the flux will be phi is equal to Li, so it will be L into I dash. Then there is a mutual inductance also. The second coil is also producing a magnetic field. Second coil is also producing a magnetic field like this, right? Current is rotating, the direction will be a bit opposite. So second is also producing a magnetic field. So there will be a flux due to second coil also. So one is the self inductance flux Li dash, and other will it be plus or minus? It will be minus, because the sense of current is opposite. So minus M I dash. So now this is the final flux. Li dash is due to its own magnetic field and minus Mi dash is due to the other coil. Why minus? Because the sense of current is opposite. So initial flux is equal to final flux, because in superconducting loops flux will not change. So now M is given as L by 2. So Li is equal to Li dash minus L by 2 I dash. So the final current when they are brought closer is equal to L will get cancelled. This will be 2I. Okay, so the current will increase to 2I. Correct now? L minus L by 2 is L by 2, L gets cancelled, 2I. So this is the second part. Now we have to write the energy. Now in an energy term, there will be half Li square also, and there will be half M I1 I2 also, because you have to take the energy, interaction energy also, and self energy also. So that's why this is an interesting problem. There are multiple concepts involved. So this current is now I dash, and this current in opposite sense as I dash. Now what is the energy? So energy is equal to, first of all, 2 times the self inductance energy, which is half L I dash square. Okay. And then there will be a interaction energy also. So interaction energy is 2 times half M I1 I2. So I1 dash, because the current is same. Now will you use plus or minus? Because this sense is opposite. The sense is in opposite direction. The current is in opposite direction. The mutual inductance energy will be in minus sign. If the sense was same, it would have been plus. So this is your final energy. So now you see there are so many chances of mistakes. So many concept has to be cleared, and there are multiple concepts involved, then there are chances of mistakes also. So that's what makes question interesting and difficult. So UF is equal to L I dash square. I dash is equal to 2i. This was your first equation. So 2 gets cancelled. I dash is 2i. So this will be 4li square minus this 2 gets cancelled. M is L by 2 and I dash square is again 4i square. So this becomes 2. 4 minus 2 is 2li square. So this is the final energy. Now we quickly get our answer. So work done is equal to final energy minus initial energy. So final energy is 2li square. Initial energy is, this was the initial energy, li square. So work done is equal to li square, and this will be your answer. So see, this is an interesting question, and hopefully you understood so many concepts from this. All the best. Bye bye.